Okay, so today I thought we would work on an interesting problem, another clearing an obstacle type problem, but this one will actually play itself forward in a lot of ways that will keep us from having to constantly be going back to calculus and other minimization techniques for other problems in the future by utilizing some interesting geometrical properties of parabolas. So here's the basic goal. We want to fire a projectile under the usual assumptions, no drag, constant uniform gravitational field. And we want to clear a wall that has a height h that is a horizontal distance L away from our launch point. Now, without loss of generality, we can, of course, choose our launch point to be the origin of our coordinate system. We know the parabola is going to follow some curved arc. Maybe the vertex should be at point P. Maybe it's after the vertex. We're going to see it actually is after. But we want to know, what is the minimum launch speed, V naught, that we should fire this projectile so that it just barely clears point P, that wall. Now, we could do this a number of different ways, but I'm going to try to do this geometrically. We can write this down in terms of calculus. Whenever you see the word minimal or minimization, you tend to think, okay, I'm going to take some derivative and set that equal to 0. That works too, but that will involve quite a bit of trigonometry and rational functions and horrible algebraic manipulation. I want to do things a little more cleverly, and we'll again invoke our AMGM inequality to try to do that. And then we'll go see a few interesting geometric properties of this minimal speed result. Okay, so first off, because we know that the kinematics here are with constant acceleration, I'm going to remind us that I can write down the position of my projectile at any time, if it starts at the origin, as my initial launch vector, which I'll label V naught with a vector symbol, times t, and then plus 1/2 the acceleration vector times t squared. That'll generally be true anytime you have constant acceleration. And we're starting at the origin, so r naught is 0. And I left this very generic. Yes, I know that the acceleration vector is actually g downwards. We'll get to that, but now I'm leaving it very general. And what I want to do here is I'm actually going to solve this equation for V naught. That might seem like a kind of strange thing to do, but we'll see why that can be kind of useful. So solving for V naught, this vector, notice I'll have to subtract this over and then divide by t. So I'll have r over t minus at over 2. You could write it as 1/2. One of the t's and the t squared gets canceled out when I divide, and we end up with this for v. What I want to do now is I'm going to square this equation, and by square it I mean dot both sides with itself. So on the left-hand side, I will get v naught squared. That's now not a vector anymore. It is just the scalar magnitude of my launch speed. And then when I square this thing out, I do have a binomial squared. So the first term will be r squared over t squared. There will be a cross term, which will be minus. I'll get 2 of them. Don't forget when you're foiling things out, you get a 2. So that'll cancel this 2. But I'll have a t over t. Those t's cancel out. Actually, you know what I'm going to do? I'm going to write this over here. So minus r dot a, that dot product of those two vectors. The t's cancel out, and the 2 cancels when I do the cross terms. And then I'm going to put my other term right here, which is the last term squared. That'll be a squared t squared over 4 when I square that out. Notice that everything we have here now is a scalar. I do have a dot product of r and a that we'll handle in just a second. Now, one thing that you can see immediately that is always what tips me off that maybe the AMGM inequality might be useful here, is that I have 2 terms that both depend on t, something I'm not really interested in. I'm trying to minimize V naught, and I don't really care about the time it takes. I've got some fixed geometric parameters. This r I can get from Pythagoras here with the L and the H, and we will in a sec, but I don't really care about t. But look, the product of these is independent of t, or t squared. So that's going to make me think of the AMGM inequality. But just to be complete, let's go ahead and rewrite this one last time. A, by the way, is the magnitude of the acceleration. We know that that's just g. And then this dot product over here, if we look at the vectors, vector r is actually vector OP. It goes from my launch point to this point P. That's the vector r. The acceleration is straight down with magnitude g. So remember that a dot product can always be written as magnitude times the cosine of the angle between the two vectors. Notice that again, my vector r is this way, my vector a is straight down. So the angle between those two vectors is actually going to be an obtuse angle. And it's actually going to be 90 plus this angle phi. So you can see that here, that if I want the dot product between r and vertical, in fact, we could even draw it in if you'd like. So let me draw a little g, which is my a vector straight down. I want the angle between that dotted line and this a. That angle is this obtuse angle, which is 90 plus phi. So I'll go ahead and write that in as 90 plus this angle phi. Now we can do a little bit of trig on this piece just to simplify it one more time. Cosine of 90 plus phi is actually the same thing as sine of negative phi. So we have a co-function identity. Maybe I'll remind you of that over here off to the side. I always remember it as cosine of 90 minus x equals sine of x, and vice versa with sine and cosine interchanged. I don't actually have a minus sign here, I have a plus sign. So that means when I do this substitution, I'm going to have sine of negative x, and that tells me that cosine of 90 plus x is actually negative sine x. That negative and that negative will actually cancel out, and I'll end up with a positive rg sine of phi, where phi, notice, is not the launch angle. Phi is the angle of elevation from the launch point to the height of the wall, point P. And I can easily use my trigonometric definition of sine to rewrite sine of phi as opposite side, which is h, divided by the hypotenuse r. So this actually, I'll just replace this whole thing here. R and R in the denominator of sine will cancel, and this is just going to be GH. So that's kind of interesting. And that's nice. We are kind of expecting some sort of GH showing up when we're dealing with conservation of energy, which is kind of what we have here. We have some V naught squared thing. However, we have not yet actually done any sort of maximization or minimization here. That's where we're going to invoke the AM-GM inequality. So look at these two terms. These two terms, when they're multiplied together, do not have a t in them. And we can just remind ourselves what the AM-GM inequality is. It says that the arithmetic mean is always greater than or equal to the geometric mean of two numbers. That will generically be the AM-GM inequality. And the equality only happens when actually A and B are equal to each other. If I rewrite this slightly, I can say that A plus B, because we don't really have a 1/2 here, but we do have a sum. The sum of two numbers is greater than or equal to twice their geometric mean. So if I apply that here, I will end up with an inequality to the right. Notice this thing will be larger than a square root. Twice the square root of those two together. So I'll write that r squared over t squared, g squared t squared over 4, and then plus the gh that's not being changed. And as promised, the t squareds actually cancel out, and everything under the radical is a perfect square, so that's kind of nice. The r comes out, the g comes out, and the 4 comes out as a 2, which cancels this 2, giving me just rg plus gh. Reading from the left to the right, we see that v naught squared is greater than or equal to basically g times r plus h. When is it minimized? Well, the inequality is minimized when this saturates, when this becomes an equal sign. So the minimum possible launch speed in order to clear this boundary is g, gravitational constant, times r, which notice is the hypotenuse of this triangle. So this implies that our minimum launch speed v naught is going to be square root of g times h plus root h squared plus L squared. That's the r from the Pythagorean theorem. So that is our minimal launch speed. Notice it's given entirely in terms of the given parameters, so that's nice. We did not need to use any calculus, just a straightforward AM/GM application. We can do a little bit more with this, though, because let's take a look at what that means as far as some of the shapes of this trajectory. So I'll go ahead and clear some of this space out. And let's notice that when this equality holds, when this inequality is saturated, remember that's the case when A and B are equal to each other. So if we're looking at this minimal condition, this also tells us that r squared over t squared should equal g squared t squared over 4. And if we solve this for r, notice we can multiply by the t squared to get a t to the 4th, take a root, and we get 1/2 gt squared in the condition of minimal speed. That's also kind of interesting because you've probably seen 1/2 gt squared before. That is the amount of distance that is covered by an object that is just accelerating with no initial speed by dropping it. In other words, let's go ahead and extend this velocity line straight up as though there were no gravity. Then what we've just proven is that this distance, which would be 1/2 gt squared, that's the amount of deflection that is caused by gravity. Right, if we only had the initial launch speed and there was no gravity, it would just follow this sloped inclined line. There would be no curvature to the trajectory. But the amount by which it is deflected from rectilinear motion is 1/2 gt squared, and we just showed that's equal to r. In other words, this segment here and this segment here are congruent. Maybe I'll go ahead and call this point r. We've just shown that OP and PR are the same distance. In other words, this big triangle is isosceles. Kind of interesting. Okay, what else might this mean? Well, if we were to drop a perpendicular to this straight line, this rectilinear motion line, we might be interested in knowing what that particular direction is. How does it relate to the velocity here? And I'll just say right now that in the next video I'll show you, this is actually a bisector of this angle and a right angle. It is also collinear with this velocity vector v. In other words, another thing that we'll show is that in the condition of launch such that there is a minimal speed getting you past this launch point or this barrier, the velocity at that point is perpendicular to the initial velocity. And that will have some interesting other consequences. As one last thing to do right now, though, we just found the minimal speed. We might want to know what is the angle that you need to launch at this particular speed. And we can see it very easily from the geometry now. Notice we have a very large right triangle here with base angle theta. Near side is L, far side is now H plus R. So we don't have to do any additional trigonometry. We can quickly see that the launch angle that gives us this minimum speed is going to obey tan theta which is the tangent of this angle, is the opposite side, r plus h, over the adjacent side, which is L. And once again, you can rewrite R in terms of H and L using the Pythagorean theorem. QED.